Okay, Lime started in 2005. There were just 3 of us originally. We were in the basement of a building, and gradually it grew up, and it got placed into Guildford in the United Kingdom, and it's grown into a world-changing, award-winning company. Successfully developed 2 field programmable RF transceivers, and there's a 3rd one that's about to be announced, I believe, in the near future. We have approximately 250 customers, though I think that may have gone up this afternoon with Ricardus. Our focus is on high performance. Okay. Our focus is on the high-performance single-chip field-programmable RF transceivers for wireless communications and software-defined radio. So if you like, it's a one solution for any frequency and any standard. Our mission is to democratize the world of RF transceivers, just as the field-programmable gate array has democratized the world of digital electronics. Traditionally, to make a mobile wireless network, you needed lots and lots of money. Then you needed a big operator to administrate it, and you needed a big self-contained wireless network to roll out your system across the land. And then you needed these very large, expensive base stations. Any sign of that laser printer? It would come in quite useful around about now. So basically, you've got these tall masts with on top of your schools frying your children. They do in the UK, and they put them in the petrol stations as well. That's the other favourite hiding place, and fake trees. So what's happened is technology has moved on since those days, and we now have very low-cost, very high-performance computers readily available. We have low-cost, high-performance radio frequency ICs, which form the front end of software-defined radios. There's been a move from the big macro cells to femtocells and picocells to increase capacity in the wireless networks. There's also widespread rollout of Wi-Fi and Ethernet and ADSL. And there's a continual advance of the open source software community, particularly pushed on by the existing SDR dongle community. So these things have kind of laid a foundation for a major step forward in the software-defined radio arena. So now it's feasible to set up your own wireless network for about $1,000. And this would typically consist of a small box with antennas on it. It's quite portable. You just plug it into your Ethernet or your ADSL or whatever you need. And you can then roll out LTE, GSM. Many of these things are now downloadable, I believe. Is it Snappy Ubuntu?
It is Snappy Ubuntu.
Yeah. So you can just download it as an app out onto the computer, and you have your radio network for you and your neighbors. Fantastic. Right. Okay, so when we started out on this path about 11 years ago, we rather naively went around to different companies and said, what do you want? And they started bombarding us with all these different requests for different kinds of systems. And you can divide them into kind of about 4 categories, I think. You have the classic data transmission systems, such as Wi-Fi and Bluetooth. You have your mobile communication systems, GSM Edge, LTE, WCDMA. You have your entertainment-based systems, such as digital television, AM and FM radio, if you have that over here, and digital satellite, and on top of that comes, careful with the laser, on top of that you have the satellite-based systems such as GPS and satellite mobile phones. And obviously you get some of the more unusual ones, such as radar, and Morse code is still very popular with the amateurs, but not so much with the mainstream communications these days. So in order to meet these wide range of applications, we need a software-defined radio. Any other approach isn't really going to work because you go down the road of doing a custom chip for each radio standard, and you get locked into that. So we bravely said, well, we can deliver software-defined radio. Then come all the horrible questions. Ricardus gets an email, a load of these each day of, can it do this? Can it meet this specification? And it's really quite intimidating in some respects. But basically, some of these come from the specifications of the radio standards. Some of these come from the way the manufacturers actually implement their particular systems. So, for example, a lot of the mobile handset people use DigiRF, which I think is over there somewhere. And obviously, the GPS people tend to use RS-232, and so on. More interestingly, what's happening is in the, where has it gone? This one here, I think it is. No, this one. The digital television people are starting to move to 4096 QAM, which is putting quite a severe stress on the phase noise of your synthesizers. So that's quite an exciting one to come out. Another one is in 5G. Everyone's suddenly talking about phased array antennas. So there's some quite exciting emerging applications coming out. So the idea is that we need a radio chip that is field programmable so that it's defined by the customer and not by the factory. There are many ways of actually implementing a software-defined radio, and it's probably fair to say that none of them are strictly perfect. There's always variations that are better for certain situations than others. The particular one we're favoring here is with the radio card as general as we can make it, but with the specific things for the application, the end user would then provide. So, for example, you would need your SAW filters, your RF switches, your PAs. So this would either be provided by the user or by a third-party manufacturer. And likewise, your computer will come largely from a third-party manufacturer. It will be stacked up with open source software, which you just downloaded. And it will be connected to Wi-Fi or Ethernet or something like that to give you external connectivity. So the radio card itself would consist of a RFIC, a field programmable gate array device for the digital side of this. So typically this would contain the data link and any additional data processing you need to be done in real time. And then you would have a USB-free connectivity here to give you the data rates that you need in actually doing a real-time radio. So some of the features of the Lime SDR, we believe it's a next-generation open-source software-defined radio platform. It's based on the 7002 field programmable RF chip, which Lime is designed. And it has the advantage that it's designed for these femtocells. So it has many of the capabilities that a classic femtocell would have. So, for example, it's capable of doing frequency division duplexing and time division duplexing. It has independent TX and RX transceivers, so you can transmit at one frequency and receive at another, or you can tune them to both the same frequency. For LTE, we've included 2x2 MIMO, so you actually have parallel transmit channels and parallel receive channels. So that might be new to some of you. We have multiplexed the RF inputs and outputs to make the RF connectivity easier. So for example, if you're doing a multi-band radio system, you can use one set of inputs and outputs, say for example for 900 megahertz, and you can do the matching networks for that. And then you can do a separate one, say for 2.1 gigahertz. The transceiver has continuous coverage from 100 kilohertz through to 3.8 gigahertz. Okay, it also has programmable analog IF filtering from about 600 kilohertz through to 80 megahertz. Some of our other parts allow you to use external filters, so you can bring that right down to a couple of hundred kilohertz for GSM. It has a programmable digital IF, which can run up to about 160 megasamples per second. It has on-chip reconfigurable signal processing. I'll go into a bit more detail about that a little bit later. It also has a FPGA, as I say, for linking and for additional processing, and a USB-free link. And I believe on the crowdsource page, it's currently retailing at $300 a board. And we're actively collaborating with the open source community to make this a success. So in previous days, you actually had to fight tooth and nail to get the software to actually work with the dongles, but nowadays we're actually helping you with the infrastructure that already exists from previous software projects. So the key feature of the Lime SDR is the LMS 7002M transceiver chip. And this basically provides most of the, well, pretty much all the features of this radio card. So one key thing is it's a relatively low power part, so typically it would draw about 1 watt of power, which is well within the capabilities of a USB power supply. I think we covered most of the things on this slide, so I'm not going to dwell on that. But if we were to take the lid off this chip and have a look inside, I think some of you may have seen the data sheet already. And there's parts of it that terrify us, so I'm sure there'll be a few things that you might find terrifying. But one of the key things is that you have 4 channels. You have 2 receive channels and 2 transmit channels to give you the 2x2 MIMO. And on each of these, there's 3 LNA inputs and 2 TX outputs, so you can actually multiplex these to match up with your various filtering configurations. We have some high-speed data converters. The ADCs operate up to about 160 megasamples per second, and the DACs operate at 640 megasamples per second. So if you just wanted the ADCs and DACs, you could buy one of our chips and then bypass the RF parts and just use them as data converters if you have some high-speed data capture projects. We have programmable IF filters on the chip, so we can actually optimize the system for Nyquist and rejection of unwanted frequency products. And of course, we have LNAs and programmable gain amplifiers as well. So it's a very high-featured radio system. So now coming back to this idea of having signal processing on a radio transceiver chip. It doesn't do everything that you could do, but it does a lot of the things that you need to do for applications such as repeater systems. So, for example, we have IQ phase and gain correction, which you need for image rejection. We have DC offset cancellation. We have inverse sync correction on the transmit side. We have digital up converters and down converters, so you can do low IF. We have decimators and interpolators, so we can minimize the traffic at the digital interface whilst making the best use of oversampling on the data converters. We also have programmable FIR filters, so you can download whatever digital filtering you need on that. On the receiver side, we have a receive signal strength indicator in the digital baseband, and we also have a digital automatic gain control. So all these blocks are bypassable, all these blocks are programmable. Another thing that we developed as a company is this Myriad RF open source community. And this has provided a way of doing the bits that you guys actually need for the thing to operate and allowing you to get on with developing fantastic SDR applications. And also, I think a number of people have developed boards as well, which I think are on the Myriad RF's website. So we believe very strongly in working with the open source community. And Lime has established a network of developers that are designing hardware and deploying affordable wireless systems. Success of these open source platforms is made possible by the configurability and ease of use of the Lime field programmable RF chip. There's been a number of applications developed. Obviously, it started out as a femtocell system, so no surprise we can do 2G, 3G, and 4G, and probably a large part of 5G whenever that's finalized. There's been interest in using the system for budget instrumentation and test and measurement equipment. I believe we recently had a demo from one of our guys of doing a network analyzer using our chip. I believe that some other people have done oscilloscopes and spectrum analyzers and so on. There's also some interest in budget avionics and navigation instrumentation. So again, this would be something that would appeal to the Americans who love to fly. I used to work with a guy who lived in Wyoming and had moose outside his office. And he occasionally would fly into the office in Santa Rosa. So he had his own actual plane. So I understand the popularity of some of these things. Ham radio, I think we met some guys who are into ham radio and frequency scannings during the afternoon. Wonderful stuff. I think some of you may be interested in drones. The Lime chip can operate in two areas in this. It can help to provide the command and control to the drone, and it can also provide streaming services. So, for example, if you have a camera mounted on your drone, you might want to feed back it as a Wi-Fi signal. There's been some interest on radio astronomy, but I haven't actually followed that one, so I don't know what they've done. I think Ricardo's been demonstrating a media streaming as part of your demo.
Yes, and some of the, on the guys who seen our demos, you can actually, if you remember, we had a box that we can do a video call stream. So on these boxes, we also can do a simple just video streaming that we can store the video on that box and, you know, just stream over the phones. So, yeah.
Okay. The other thing we've been getting involved in is the Internet of Things. I believe some people have developed a utility meter application for that. And I think another person has developed tire monitoring, tire pressure monitoring. There's also been some interest in radar and computer peripherals and so on. So this list is continually growing as people find more and more ideas. So going back to democratizing wireless networks, what people often like to do is just simply buy a box and download the software and just get on with it. Other people like to do it the hard way, such as myself, but each their own. So we have this LTE system here with a 10-watt PA, which I... Ricardo, do you want to talk about that?
Sorry.
Because you know more about it than me.
So, again, we were using some off-the-shelf PC that you can buy for $300, $400. We were using as well the PC Express board connected to one of the slots. To extend the range, we were using 10 watts PA. As you can see that metal thing, and if you can just get a pointer. So that was a 10 watt PA connected straight away to, I think that was going to a duplexer, and actually no, it's actually going to straight away to PC Express and then going to duplexer. So we were running as well LTE stack on that, and well, we couldn't be close to the box with such 10 watts output power, so that's probably gonna melt your brain. But it should get quite decent range. I would say 3 kilometers or something like that.
Okay, do you want to say anything about these guys?
Right. Okay. Again, these boxes are on our display today. So they are something like femtocells that they are using USB interface LimeSDR cards. These ones. So the main idea here that using that concept that you have flexible radio and the flexible really computer power. You can scale these base stations to anything you like, from 4G base station or 3G or 2G, depending on your communication needs. Yeah, and probably the main board that we're trying to demonstrate use this USB 3, well, USB powered LimeSDR, which, as you probably know, that we went for crowd campaign, and we were successful. So we're going to start shipping them in the end of this year. So you can join. Still, you can go and buy if you like it.
Okay. The other thing that's quite interesting is that this board over here has the capability of doing adaptive digital pre-distortion. So some of the power amplifier people like to use that to get the best efficiency out of their PA systems. Okay, we're also supporting third-party designs when we can. So this is an example of a board done by Fairwaves, and it's a mini PCI SDR radio with one of our 7002 chips on it. It's 2x2 MIMO, has all the features of the 7002, but it also has a GPS disciplined oscillator on board as well to meet the timing requirements of things such as LTE and TDD. Okay, we're now going to move on to a detailed example, which hopefully you won't find too terrifying. So you have permission to cover your eyes if you find it too scary. Basically, we're looking at doing GPS reception on a LimeSDR card. So the first thing to start talking about is that radio systems rarely exist in isolation. And increasingly, we're seeing that people not only want GPS, but they also want to do Wi-Fi, mobile, and so on. And you may also be unfortunate enough to be next to a large TV transmitter. So this leads to a situation where you can have some really large signals, such as a TV transmitter at 100 kilowatts ERP, whereas your GPS signal is actually about a femtowatt. So that's a massive, massive dynamic range. So more reasonably is GSM handset would be something like 2 watts effective radiated power, worst case. A typical Wi-Fi system would be about 20 dBm, which is 0.1 watt peak. And obviously WCDMA and LTE are going to be sort of similar sort of power levels. So the GPS signal which we're interested in is not only is it small, but it's also actually buried in the noise floor of the system. So you've got a very challenging reception system. And there's a number of features in the Lime chip that make this easier, but you also need a SAW filter to keep out all the bad guys. And most GPS antennas would probably have a SAW filter within them. It's difficult actually getting the data from the datasheet sometimes. So some of the features in the LimeSDR or in the 7002 which make it very good for these challenging reception situations is the low noise figure, the low far out phase noise, relatively high 1 dB compression point, and good second and third order intercept points, and also it has quite a lot of bits on the ADC. So a classic GPS receiver would only have 2 or 3 bit ADC. so it has very little room to cope with a large interfering signal. Whereas the Lime SDR chip is a 12-bit device. So you actually have plenty of bits for large signal interference. The other issue with processing GPS signals is that they're rather large. Basically, to get sufficient information from the satellite signal to decode your position, you need about 30 seconds worth of data. And you normally sample at something like 2 mega samples per second. And with a 2 times 12-bit words per sample on a shared bus, this is coming out at something like 98.2 megabits per second data rate, which can be comfortably handled by USB 3, but USB 2 wouldn't be able to handle that data rate. So if you're just doing the 30-second data grab for the 5 subframes you need for GPS, that's corresponding to something like 123 megasample data set to process. So that's not too bad, that's quite reasonable. If you went for the full 25 frame data set to get the LimeNET data, then you're looking at something like 3 gigasamples of data, which is quite a commitment. Having said that, getting cheap memory these days is not such a problem, so it is becoming very feasible. But there's a need to actually minimize what comes out of the Lime chip so that the software isn't buried in numbers. Okay, this is one of the frightening slides, so feel free to cover your eyes. Basically, when I set up this example, I did an oversampled low IF receiver. There's some good reasons for doing these things. Basically, when you calibrate a 0 IF transceiver, you still have some residual DC left. And in most cases, this doesn't really matter very much. But for very sensitive applications such as GPS, this begins to limit your sensitivity of your transceiver. So by moving over to low IF, you avoid the residual DC. And you're able to get a couple more dBs of sensitivity. Another thing is that the data converters, if you use oversampling with a data converter, you effectively get some extra bits. Every time you double the sample rate over what you need, you get one more digital bit. So because we're using such a system, we're using a 3 megahertz IF filter. So our low IF is about 2 megahertz, well, 1.5 megahertz offset. And then we use our digital conversion system to down-convert this to baseband. And I'll go into some detail of this now. So you remember earlier I showed you this really frightening diagram with lots of boxes on it. I'm now going to show you which of these boxes I'm using for GPS. Right, so we have an external antenna, LNA and SOL. We have the front end RF set up for a particular configuration. And then we're making use of the various digital blocks here. So we have an internal clock generator, which is generating our timing, which is locked to the reference crystal. We have the ADC running at a quarter of this speed. We have image rejection correction blocks here, which reject any image band signals. We have a digital down converter here running at 1.5 megahertz with a complex mixer. We have times 32 decimation. So this is taking our 65 megasamples per second and turning this into 2 megasamples per second. So we dramatically reduced our data into the computer at this point. We also have a FIR filter to help with noise filtering. So the FIR filter, we designed it using a script written in Octave, and it generates all the coefficients and writes it into a convenient file. Okay, so now we get to the nice picture. And basically, we're using a antenna mounted on a ladder in my back garden here. stuck down with tape. Is a north-facing garden, so the house is obstructing some of the views of the satellites, but I extended the cable sufficiently long to see enough to make this system work reasonably well. So here is the scan of the satellite code. So there's 32 possible codes, and we're receiving 7 satellites, and this one here is probably just too small to decode. So we're actually getting 6 usable satellites. This is the recovered data from one of the satellites. This is some diagnostic information, which I won't go into today. And then we have the exciting diagram here, which is the location of the satellites and my location. So you have longitude along here, and you have latitude here. So the equator is here, if you like. The North Pole is here. The South Pole is here. And the Greenwich Meridian is somewhere around there. And you can see the 6 satellites that were received. And you can see there was one that we calculated from the almanac position. And as you can see, it successfully decoded the satellite information. So I don't think we got sound on this, but this is a basically an LTE overhead projector. And basically the video is transmitted via the LTE, and it's then decoded and demodulated and then displayed on the overhead projector using the projector unit. Do you want to say anything more about that, Ricardo?
So again, anyone who has been on our site, actually they probably seen this projector running. Again, it's using our LimeSDR board, which is connected to via USB 3 to that CPU, and we are again running LTE, open source LTE stack over there that enables us to connect these phones to that projector. So it works like a concept that you can pretty much use that LimeSDR in any device that has a bit more processing power and enables you to do some kind of communication link. If you want to see it, you still can come to our website, stand, and we can demonstrate that for you straight away.
Okay, just a quick summary to say where we got to. Through a combination of advances in low-cost computing power, low-cost field programmable RF devices and digital devices, and the availability of open-source software and internet connectivity, it's now possible to design low-cost software-defined radio wireless networks. We also looked at a real-world example of using GPS on a LimeSDR card, showing how the field programmable RF can lead to an efficient high-performance implementation of a software-defined radio with minimal external components. I forgot to mention there's an external bias T, which is powered from the LMS 7000, the LimeSDR card for the GPS example. We believe software-defined radio is all about participation, and we continue to invite you to back our campaign on the Crowd Supply website. Okay, so that's the end of my talk, and you're now free to ask any questions if time allows.
So with regards to Wi-Fi, for instance, the FCC recently has been pushing, they have a proposal out to push down regulations on Wi-Fi routers to limit essentially the Wi-Fi manufacturers have to say how you can avoid or how they can prevent the firmware from being changed to isolate the radio to specific power requirements within specific frequencies. I mean, obviously, with your device, you're kind of all over the place, which is kind of the point of your device. So, I mean, are you participating in that FCC discussion? Are you aware of it? Like, usually what the U.S. does, other countries do, with returns to safety. I mean, there's one thing if it's, I mean, you do happen to be talking to a room full of hackers. So, I mean, I'm just curious, like, have you thought about that and how that affects you?
Yeah. Well, thank you for the question. Well, basically what we do is just trying to get this LimeSDR board to anyone so they can play around with anything what they want. Have we discussed with FCC about this? No. And we are not participating in any discussion with FCC. Thank you. Is that the way to go? Probably. But what we're looking for is to, as that presentation says, we need to think about easiest way to use our wireless communication links. And I think that LimeSDR is that where LimeSDR comes as a hardware that enables you to use any open interface in the air.
To provide more perspective, I think the FCC guidelines only affect a specific portion of the 5 gigahertz spectrum, and 5 gigahertz is above your range. Secondly, research and testing devices are excluded. If I remember correctly, please check the guidelines.
Right, yeah.
Can you repeat that?
Yeah, can you repeat that?
Yeah, I think that it's only covering a certain portion of the 5 gigahertz spectrum where DFS radar is, and you guys aren't within that frequency spectrum. Secondly, I think that testing and research equipment is excluded. It was largely to commercially available devices.
Yeah.
Okay, just to add a few comments to that. The issue of power detection, it comes up quite often in other radio standards. And the way it's normally handled is you would have a directional coupler after the power amplifier. And you would either use a power detector chip, such as one of the ADI devices, or you can use one of the transceivers to measure the RF power being fed back.
You mentioned open source. Are you working with such developers for applications like SDR Sharp and New Radio?
Yes, we do have support already for GNU Radio, and the board just recently, has been available for people. So yes, there will be a lot of things to come.
Data sheets, full access to data sheets without NDAs, are they available? Source code for bit streams for, looks like you've got an Altera up there, is that available, or is that something that you're keeping internally to yourselves, or where are you going to take the design kind of going forward?
Well, Lime Microsystems as a company, we always supported open source initiatives. So we've been open, I think, since when we created the company. These guys created the company. So yes, data sheets are available to anyone. There are a lot of technical documents in our website, limemicro.com, that you can get. There are a lot of discussions in myriad.org around our transceivers or our boards that are being developed with our transceivers. And in terms of open source, well, it's probably, the name says everything, right? So if there's open source software, you have to have documentation about it.
So obviously you're focused on shipping this version of the product, but kind of what are some of the things that you might be seeing 18 to 24 months out for like a version 2, some things that you're backburnering right now?
Yeah, so the second thing that we want to do, well, first thing that I want to do is try to establish the production line for LimeSDR board. Second thing after that is accomplished, we're going to release the board, which will extend the frequency range up to 12 gigahertz.
So I'm a complete noob to radio. It's all fascinating, but I know next to nothing. So 2 questions. One, For the Lime SDR, is there a kit that I can get for like everything else, right? Like everything that sits between the antenna and the board, just to get started. I know if I were to be serious about it, I would need to like design my own stuff there. And the other question is, you talked about how the Lime chip is low cost. What does low cost mean in comparison to your competitors?
Okay, thank you for the question. So in terms of the kit, if you go to our limesdr.org website, you will find modifications of the board that you can buy. So you can buy the with the package. You can buy just bare PCB. You can buy antennas, cables, different type of cases. So there are things to choose from, right? And the second question was, okay. So yes, we are really competing with a company called ADI. ADI has similar transceivers. I'm not sure if they are open as we are. And in terms of price, well, probably can go in DigiKey and find out, right?
Okay, thank you.
How many of the folks here attended back at H2K2 2002, the GNU Radio at USRP demo and talk? All right, so it's been 14 years since then. So we have a community here of people that are really interested in this, and this obviously is really leapfrogs that. I mean, GNU Radio and USRP is still around, is being used for some amazing applications, but this appears to me to be almost a paradigm shift in how far we can push the envelope in this. How many people in this room have some form of SDR other than what's in their phone? Wow. Other than what's in their phone. What's that? So that's a lot of SDR adopters here. How many of them how many people are using them for monitoring HF, shortwave reception? Okay. Can you just hear some of the other applications people are using SDRs for that are interested in using this platform for? Spectrum analysis? I'm sorry? Oh, okay. Flight data. Satellite communications. Television. Digital television. Open source cellular. LTE. What other things? MASH, point-to-point microwave. Mesh networking. I'm sorry? Security research, of course. Okay. So, I couldn't hear him. But so from a standpoint of getting into this, the crowd supply is the source where people can purchase the hardware from, right? And the availability is what on this? You've gotten the crowdfunding you've needed, and you're moving into full production now. So when can people expect to receive their hardware that they were to get on order on crowd supply?
Yeah, we committed to end of November. Okay. So we committed to deliver a Lime SDR board to backers and anyone who's gonna back now by the end of November this year.
Okay. So this is not vaporware. This is real. You can see it downstairs, and this is going to be amazing. So in the next, sometime in the next few months, next year, we're going to see some really interesting applications. And is there some sort of contest going on you have for awarding people to come up with the best ideas?
Yes. So thank you everyone who has participated in that. I want to say there were very huge and very interesting ideas that you come up with. I think the winners already had to get some email, so saying that who has won Lime SDR. So please come in to our stand and get Lime SDR right now. Thank you.
Downstairs in the vending area, right at the bottom where the express elevator is where their table is. Great.
Thank you.
Great job. Great job. See, a lot of SDR radar adapters. Good stuff. You don't have to rush. You still have plenty of time if you want to take some questions.
I have the same one. I'm waiting for the flash to crap out, but it has the app. I'm assuming that board would be awesome for intercepting signals and transmitting
On your mail address, like, thing already. Yeah, I know.
I mean, you can tinker with it. I haven't seen much stuff designed for RFIDs.
I mean,
But there's a lot of tools for Proxmark.
Does that use facial or does it use
It can use whatever the tag uses because it has its own FPGA.
Okay. I'm just kind of curious what most of the tags are using. I'm excited to know if it's open to All right, no.
Yeah, absolutely. Actually, something that you may be interested in is something called the Proxmark Pro, which is basically because the Proxmark